Okay, can you guys hear me? Okay, all right. Okay, let's get started. Okay, we are still in the middle of polysilicon to monocrystalline conversion. So we stopped halfway last week, and we have discussed that we're gonna go through the calculation today on this page. So you can see the slides, right? Confirm. Can see the slides. Okay, all right. Okay, so have you guys gone through the calculation, the question? That's right. Let's go through the questions 1 and 2. So I'll get somebody to show your workout on these two questions. Right, so let's go to the first one. A silicon ingot which should contain 10 to the 16 atoms per cm cube, known by ZAT technique, so Jagroski process. So what concentration of borons should be in the melt to give the required concentration in the ingot? Okay, so the ingot should contain 10 to the 16. It's doped by boron. So now we're gonna need to find out what's the concentration of boron needs to be incorporated in the melt during the growth process. Okay, so what's your answer? Anyone? Put in the chat box there. What's your answer for the first one? Or I'll just go through the name. Okay, hold on. Anis Shahira. Okay, Anis Shahira. So please share your answer for this question, the first one. Anis, can you hear me? Not done yet. All right. Shazwani. Ilham, okay. 125, 10 to the 16. Ilham, Faika. Right, 1.25 times 10 to the 16. Okay, how did you get that? How did you get 1.25 times 10 to the 16? What do you use? Can you Ilham, right? Ilham, can you unmute yourself? Maybe you can verbally explain how did you get that? Okay, okay, louder please. Okay,
So
all right.
times power of 16
Okay,
divided by 0.8.
divide by 0.8. Okay, why is it 0.8?
The segregation coefficient for boron.
Okay, so the equation is K naught.
K naught equal to the concentration of solid over concentration of liquid.
Okay, so K naught is equals to CF over CL, kan?
Yes.
So we're gonna find out CL, right?
Yes.
Right. So it's equal to 1.0 times 10 to the 16 over 0.8. So we end up with 1.25 times 10 to the 16. Okay, good. Done. So the CL in this case is 1.25 times 10 to the 16 atoms per cm cube. Done. So let's move on to the question number 2. Question number 1, okay, semua orang paham? Anybody didn't get that? Just go back to the equation. Anybody didn't get that? You can tell now. You can go back to slides. CS over CL. Right, so okay, so let's move on to the second one. Second question. Who's here? Go Chingwei. Chingwei, would you like to share your workout for second one? All right, you don't know how to do. Okay. Anyone has done the second part? Izyan. Izyan, have you tried? If the initial load of silicon in the crucible, okay, so Izyan share. Initial load of silicon in the crucible is 6 kilos, so 60 kilos of silicon. How many grams of boron? Atomic weight is 10.8. Okay. How many grams of boron should be added to be able to produce the required concentration in the ingot? So the density of molten silicon is 2.53 gram per cm cube. Okay, Izyan, what did you get? You just share, unmute yourself and you explain the answer. Then we go through the workout. 0.034 gram. Okay, anybody else got 0.034 gram? 0.034 grams. So that means 1, 2, 3. So that means 34 milligram, right? 34 milligram. 5.31 milligram Ain Natasha, 5.31 milligram Ilham. Okay, so hold on 1 second. Okay. Lecture, let me open the crystal growth final. Okay, hold on. .31. Okay, 5.1. Okay, it's 5.31 milligram. Right, maybe Natasha, would you like to share your workout to 5.31? You can unmute yourself and then explain, then we'll go through the workout. Or you want to share your content? You can also share your content. Share your page.
I thought
Okay, so you try to share your content, or you just say verbally? Okay, go ahead.
So first we have 60 kg. So first we need to volume.
Right.
So
okay, convert to volume.
Yes. So
okay, how did you do that?
Mass over density. So we got the, and then next we need to find the number of atoms.
Okay, hold on. So what volume did you get after the conversion?
2.37 times 10 to the 4.
All right, 2.37 times 10 to the 4. So that's given by density is equals to mass of volume. So we know the mass. we know the density, we don't know the volume, so we work out the volume. So we get the V 2.37 times 10 to the 4. Okay, next.
Next, we need to find the number of atoms. So
Okay.
the before we got
Okay.
in the molecules, we
Okay.
times the volumes.
Okay, so how did you do that?
So 1.25 times 10 to the 16 time with the
So
volume.
that's given 1.25 is the CL, right? The one that we calculated in the first part.
Yes.
Okay, then times
Times
the
the
volume.
volume.
Okay.
Then we got
You
2.96 times 10 to the power of 20.
okay, 2.96 times 10 to the point 20. What's the unit there?
Boron atoms.
Okay, boron atoms. Okay, so that's the number of atoms. Okay, next.
Then we need to find the gram weights, right? So the
Okay,
mass
right.
number of atoms um time with atomic weight over
Okay.
Avogadro.
Okay, times the atomic weight over Avogadro.
Yes.
So you got 5.31.
Yes.
Okay, apa semua orang dapat tak? I need to share this anyway. Let me just share the one that Ain and I think Ilham also work out. I think probably the same way to get to the answer. So let me share the page of the solution. Share content. Where's the page? Yep. Right. Can you see the PDF file now? Nampak tak PDF file saya share? Okay, good. Alright. So let's go to the first one yang tadi kita recap balik ya. Nanti I'm going to share this on Elan. Okay. So the first part is study K naught is equal to CS over CL. So we need to work out the CL. So then it's given by 1016, which is the CS in the ingot over 0.8 segregation coefficient of boron. So we got 1.25 times 10 to the 16 boron atoms per cm cube. Done. So the second part, we need to work out the weight of borons required in order to deliver the concentration that we just calculated in the first part. So how do we do that? First, as I explained just now, so we know that the weight of silicon is 60 kilos, atomic weight is 10.8, density of molten silicon 2.53, Avogadro's is a fixed constant. Right, first we convert we need to find out the volume based on density is equals to mass over volume. So we know the density of silicon 2.53. Mass is given 60 kilos, but we have to convert into gram. Okay, so kita dapat volume dia 2.37 times 10 to the 4 centimeter cube. Then we need to calculate the total number of boron atoms in the melt based on the calculated volume. So that's given by the value of CL because it's the value of the melt, right? CL calculated in the first part, 1.25 times 10 to the 16 times the volume. Boron atoms per volume times volume will give you boron atoms, right? It will cancel out the cm cube. So you're going to end up with 2.96 times 10 to the 20 boron atoms. Then so you need to use the given the answer there 2.96 times 10 to 20 times the atomic weight given there of the boron, right? Atomic weight 10.8. So over Avogadro's number 6.02 times 10 to 23 atoms per mole, it will cancel out. So you're going to end up with 5.31 milligram of boron. Okay. So 5.31 milligram of boron will eventually give us 1.25 10 to the 16 boron atoms in the melt and 1.0 times 10 to the 16 in the ingot. So it's going to be p-type with 1 times 10 to the 16. Okay, so okay, semua clear? Can you understand the workout? Is it okay? I'm going to share later on the PDF file on eLearn. Yang second part tu panjang sikit, but the first part is quite straightforward based on the equation that we've learned last time. So this, if this one appears in the exam, then it usually carries up to 20 marks. Okay, 20 marks. Usually it's maybe 5 in the first part and 15 in the second part. So altogether 20 marks. So you have to know how to calculate to get to the boron atoms. Or the question can also be tweaked for you to find something else, but boron atom, boron weight is given. So you might have to calculate something else, right? Just a tweak of equation. Okay, so let's go back to the slides. So done. You can see the slides now, right? So I'm switching to the slides now. Okay, okay, good. All right. Last week, right? Yeah. Last week we have covered up to Czochralski growth or ZAT silicon. So now we look at float zone silicon or FZAC silicon. So float zone silicon is a process based on zone melting principle. Some call it zone melting crystallization. Some call it zone melting recrystallization. One of the common names of this process is called ZMR. Let me type down zone melting recrystallization. Right, ZMR, zone melting recrystallization, because what it does is it melts by zone along the ingot in sequential form, right? So used to produce extremely pure silicon. So it's in terms of purity is purer, if you like, than Czochralski silicon. So polycrystalline rod of ultra pure silicon is passed through RF coil heating. So you're gonna have a RF, you're gonna have an RF coil neck. So you have an ingot, and then we're gonna have an RF coil neck going through like this. It's going up in order to repurify and recrystallize the silicon by zone, right? Creates a localized molten zone which the crystal ingot growth. So it's called localized molten zone. So it doesn't melt the whole silicon ingot at one time, but instead it goes by zone. So a seed crystal is used at one end in order to start the growth. So it uses the same technique like Czochralski, in which a seed is incorporated at one end in order for the growth to follow the orientation. So the molten zone, okay, the molten zone carries away the impurities as the process goes on. So that means when the process is going on, so it actually carries away impurities within the molten zone. So bila dia makan, maksudnya impurities dia akan follow dalam molten zone tu to the other end. So basically we are also carrying impurities to one end to be purified, to be removed. Okay, saya akan tunjuk kat you one YouTube video from UNSW. So the molten zone carries away the impurities, purifying the crystal, difficult to do. So the moment we are melting, we are bringing the impurities in the melt, we are also purifying the crystal, leading to crystal with high purity. So process is carried out in evacuated chamber with an gas purge. There's no crucible, it's just an RF coil electrically activated. Expensive process, only used when oxygen and carbon levels cannot be tolerated in the ingot. So we have discussed in the ZAT process that there will be incorporation of oxygen and carbon due to the mixing of the impurities at the edge of the crucible, which migrates into the silicon melt during the process, but that can be minimized by using a magnetic coil to minimize the mixture, to minimize the migration of the impurities into the central region of the melt. But this one, if you even would like to purify the ingot from oxygen and carbon, so especially when your applications intend to have a very low level of oxygen and carbon, FZ silicon can be used instead. Okay, so it looks like this. We have a gas inlet, inert gas. So we have an ingot in the central region, and then you have RF coil attached. So RF coil is what we call sort of wrapping the ingot, and it's moving along the way. So on the right hand side there, you can see where we have seed crystal at the bottom of the ingot, and then right above the seed crystal we have a heating ring, which is powered by the RF coil. So it's called induction heating ring. So this heating ring will actually move along the ingot and melt the ingot by zone. So that's why we call it zone melting recrystallization, because it's actually crystallizing the silicon as well to produce monocrystalline silicon. So it moves along the way from the start until the end. So it goes from the bottom to the middle and then to the top region. So it looks something like this on the bottom right figure. So you can see bottom right figure where the heating coil is, where the heating is actually happening, or zone melting crystallization of the ingot is actually happening. So let me show you a video by UNSW, a short one, to show how does the FZ process works. So let me share with you the page. Hold on, yep. Let me share the content. Okay. Right, can you see the YouTube page now? Nampak tak YouTube page yang saya share? Okay, good. Right, so I'll just play this one. It's just 23 seconds video. So we can see here how the RF coil heating works for the FZ process. So the seat is at the bottom. The RF coil neck is there. So it's actually moving. So heating the ingot by zone from bottom to up. So impurities are actually being brought to the upper end of the ingot, and then is end up there, and I'm going to slice, I'm going to cut the edge, the upper edge of the silicon ingot for it to be completely removed. Let me just repeat the video. You can watch this later on. I've already uploaded the link on Elan. Okay, good. Let's go back to the slides. So the impurities are preferentially removed by the melting process, along the melting process. So they are sort of trapped in the molten region. So they move to the upper side of the ingot, and then we're gonna cut it off, and then they're gonna be removed from the ingot. Okay, this is how it looks like as well. Another representation of the process. So we have induction coil, we have ingot, so we have seed crystal at the bottom part. So we have other coil moving. So you can see from the left hand side and from the right hand side as well. So induction coils there. So FZ crystals are doped by adding doping gas like phosphine for phosphorus to make it N-type, or dibrane gas B26 to make it P-type. Yep, in order to do the doping during the process. So unlike CZ silicon, the silicon molten by FZ is not in contact with any substance. So in this case, you can notice that it's not in contact with any phase, because it's just moving along with the ingot, but it's not touching the ingot actually, right? In comparison to the ZAC process, where the molten silicon is actually in contact with the wall of the crucible, so that leads us to the formation of oxygen and carbon, and migration of certain impurities into the molten silicon. So being contactless makes the FZAC silicon higher impurity. So that in terms of the purity of the silicon wafers at the end, because it doesn't have any contact during the process. So therefore, FZAC silicon can easily achieve higher resistivity, higher purity, and higher resistivity after the process. So additionally, multiple zone refining or the FZAC silicon can be performed on a lot to further reduce impurity concentration. We can also enhance the purity by that. Segregation coefficient plays an important role. So we know that K0 for boron is 0.8, K0 for phosphorus is 0.35, but phosphorus suffers one problem during the process where it actually evaporates from the melt at fairly high rate. So causing the silicon to be less uniform in terms of doping level across the ingot. So that's why it's a lot harder to produce more uniform N-type silicon in comparison to P-type silicon, because phosphorus evaporates during the process. So comparison of CZAC versus FZAC, right? If you look at Czochralski, it allows big crystal diameters. So state of the art, the latest one is actually up to 18 inch or 450 mm. But the equipment, the production line, the wafer fab itself has to be a wafer fab for 450 mm fabrication. So compared to FZAC, lower production wafer. So CZAC is slightly cheaper in comparison to FZAC silicon because of the purity. And if you look at the disadvantages, so CZAC has high impurities, so oxygen up to 18, carbon up to 18 as well. So in certain applications, this cannot be tolerated, right? But in some other applications, this level of 18 is okay. So, well, it depends on what type of applications do you want to use the wafer for. So if you can, the device is not sensitive enough, then CZAC is fine. If the device is very sensitive to the impurity level, then you need to go for FZAC. Okay, low homogeneity of the axial and radial dopant concentration in the crystal caused by oscillation in the melt during crystal growth. So after we've done with the process, we need to remove the edge of the silicon ingot, because it might not be homogeneous. So it needs to be, we'll see later on when we talk about wafer preparation, we need to cut to make sure that it's completely round in nature. So you cannot have some ridges or roughness at the edge, because it's going to affect the fabrication process, especially when we talk about robot arm handling during processing, because the robot arms are usually moving at high speed, whether it's X or Y or Z or theta. So the handling needs to be perfect. So therefore, the wafer preparation, the roughness at the edge needs to be completely removed. So if you talk about the advantages of F process, so it usually gives us low impurity concentration due to the non-contact nature of the process. So in particular, oxygen carbon concentrations are much lower as compared to CZAC silicon, since the melt does not come into contact. So it's due to the contact problem. So the moment you have contact, you're going to have higher impurities. So with no contact, we're going to end up with low impurities. So there's no hot graphite container being in contact with the molten silicon. So dopant concentration in the final crystal is more homogeneous for FZAC, which allows very high ohmic wafers as well as wafers with narrow specified electrical resistivity. So when you talk about doping concentration uniformity across the ingot, FZAC is more uniform than CZAC silicon, because one of the reason is that the crystallization process takes place by zone, and plus as we melt the zone, so we also carry impurities along until the very end, and then they are removed. So impurities are a lot lesser, and then the doping level is also more uniform in FZAC in comparison to CZAC. However, the disadvantage of FZAC is more expensive to Czochralski process, and the crystal diameter is limited to 8-inch, unless I don't know what's the latest innovation or the latest setup for FZAC. You might want to find out. FZAC silicon diameter, I don't know, perhaps it's gone up to 450 mm already, but of course it's going to be a lot more expensive, because at 8-inch 200 mm is already more expensive than CZAC silicon. So if you talk about FZAC at 450 mm or 18-inch, it should be a lot more expensive. Okay, the doping, we have discussed a couple of times already, including in 386 last time. So when we do the growth, you can either leave the silicon intrinsic, because there is always customer market, if you like, for intrinsic silicon. So you can also fabricate N-type silicon and P-type silicon, and N and P-type can also be very lightly doped, if you like. If you look at the table there, so it can be very lightly doped, where the doping level is less than 10 to the 14. So when you see the double negative there, it's lightly doped, so less than 10 to the 14. If you talk about lightly doped, it's usually 10, 14 to 16. So N minus or P minus. So the typical range is 16 to 18, if you like, 16 to high 18. So it's usually labeled as N or P. There's no plus or negative sign on the superscript on the P or N type. But this one is, I think, it's quite loosely used. So some people, they describe lightly doped as N instead of N minus or N plus. So when you see it's either N or N minus or N or N plus, you have to really see the description that comes along with the note, because I've seen people use the notation quite loosely, so there's no fixed range of the dope or lightly dope. But when you talk about heavily doped, it's more straightforward, because you will tend to see N plus or P plus as a superscript on the N or P. So in that case, they mean heavily doped. It's usually more than R1E19. We'll normally see N plus plus, P plus plus as well, especially if it goes up to nearly 10, 20. Even though there's no fixed range, but that's normally the what I call the typical convention being used by researchers or by industry in this field. Okay, so when you talk about growth, you can either grow intrinsic, you can either grow P type or N type, or double negative or double positive, depending on what do you need. So as if you talk about a supplier, being a supplier for Czochralski or float zone wafers, so I believe they can always tailor the resistivity or the doping level of the dopants in the silicon ingot to the customer's needs, right? Either the customer want intrinsic or heavily doped or lightly doped. Oh yeah, done already. Okay, so we're done with crystal growth. So this part we have covered polycrystalline to monocrystalline conversion. So essentially it can be done by two processes, either one. If you want to go for the standard one, then it's your Czochralski process or CZAC process. If you want a higher purity version of the silicon, particularly oxygen and carbon, and in fact others as well. So you can go for float zone, but float zone is more expensive because it's a non-contact process. But Czochralski is a contact-based process with the hot crucible, which end up with unwanted migration of impurities into the bath. So that's the essence of this topic. Segregation coefficient. So the higher K0 have, the more uniform it is. So the higher the chance your dopant is going to end up into the ingot. If your K0 is low, then on the lower the chance, the dopant is going to end up into the ingot. So that means you have to put more, but you're going to have less in the ingot. So that's the implication of K0. All right, any questions so far about this process? Is everything okay so far? Semua okay ke? Can you guys follow so far? Okay ya? Tak ada jawapan means okay. Okay, so far so good. Okay, later on I'm gonna upload the solutions now. Revise the calculation based on the document. You can go through later on. Kalau you miss or you don't understand some portion of the workout. All right, so the next one will be tomorrow. Okay, minggu ni kita akan go through new timetable kan. So tomorrow the class will be 10 a.m. Hold on a second. Okay, so yep, it's at 10 a.m. 10 to 11. No class on Wednesday. Will be 2 to 3. Friday will be 11 to 12. Okay, so this week we're gonna use the new timetable as in the course introduction slide. Okay, if there's no question, then yeah, that's it for today. I'll see you tomorrow, inshallah. Bye bye. Take care. Assalamualaikum.